In this second part of the video, we're going to take a look at different information that we can get off the unit circle. And so if you're following along the PowerPoint, you'll see these slides go beyond here. And so that's where I'm getting my questions from. So the first thing I want to take a look at is domain and range, which we can do for a trig function, right? Cosine and sine, they both have a domain and a range. Remember, the domain is the input, so those are the x's. The range is the output. So if I'm talking about domain and range, the input in this case is going to be the angle measure. The output is going to be either the cosine or the sine. So I'm going to take a little corner over here. I'm going to talk about domain and range. So for the sine function, the domain, remember, is the angle. So look at the angles. They start at 0, pi over 6, pi over 4, pi over 3. They keep going all the way to 11 pi over 6. But then I can keep going beyond 2 pi, right? I can go around the unit circle again a second time, 4 pi, 6 pi. I can even go backwards. I can go from 0 to negative pi to negative 2 pi to negative 3 pi and so forth. So the domain for the sine function is all real numbers, which we can abbreviate like that. But look at the range for the sine function. Remember, the sine is the second coordinate here. So it goes 0, a half, root 2 over 2, root 3 over 2, 1. Then it starts coming down again. Comes down to 0, goes down to negative 1, and then comes back up to 0. So the range for the sine function is between negative 1 and 1. The sine will never be less than negative 1. It will never be greater than 1. But it can be negative 1 and it can be positive 1. That'll happen at pi over 2 and 3 pi over 2. Similar issue is going to happen with cosine, because I can put in any angle measure that I want. But what's the range that's going to come out of cosine? Remember, cosine's the x-coordinate, so it starts at 1. It goes down to 0. Then it goes down, I'm looking at those first coordinates, it goes down to negative 1. Then it comes back to 0. Then it comes back to 1. So the cosine and sine both have domains of all real numbers, but they have ranges between negative 1 and 1. All right, the next question that I'm going to ask is about odd and even functions. So every even function says that you can put in the opposite and get out the same thing. So one of these trig functions is even and one of them is odd. So the question I said is, which one, if you put in a pi over 3, gives you the same answer as if you put in a negative pi over 3? Well, where's my pi over 3? Here's my pi over 3. All right, so here's pi over 3. Here's negative pi over 3. All right, 5 pi over 3 is the same thing as negative pi over 3. Between these 2 points, is it the x's that are the same or the y's that are the same? It's not the y's, right? Here's root 3 over 2. There's negative root 3 over 2. It's the x's that are the same. So if I put in a pi over 3 or I put in a negative pi over 3, I still get a half either way. So if that's true, then cosine is an even function. Now, what about an odd function? An odd function says that if you put in the opposite, you get out the opposite. Well, process of elimination. Look, if I put in a pi over 3, I get root 3 over 2 for sine. If I put in a negative pi over 3, I get out a negative root 3 over 2 for sine. So sine is the odd function. And I think in the next unit when we graph these, it'll make it even a little bit more apparent as to which one is the odd one and which one is the even one. But for now, we can simply look at it in terms of definition. Putting in the opposite returns the same thing. That's even, that's cosine. Putting in the opposite returns the opposite. That's odd, that's sine. All right. What else is even besides cosine? Well, the reciprocal of cosine is secant. So if cosine's even, secant's even also. You can see I stole this from the textbook. And then sine and tangent are both odd. We'll get into a little bit more why tangent is odd when we graph it. If sine's odd, then cosecant's odd. If tangent's odd, then cotangent's odd. Let's take a look at these. Given the sine is 3/4 and theta is in the second quadrant, find the other 5 trig values. Well, the sine is 3/4 in 2 different places, right? Sine is opposite over hypotenuse. And what this is saying is that both the opposite and the hypotenuse are positive. Well, the hypotenuse is always going to be positive. So if sine is 3/4, then, and I'm in the second quadrant, I'm looking at a triangle like this. There's my theta. Sine is opposite over hypotenuse. So opposite is 3. Hypotenuse is 4. Now I got to figure out this third side down the bottom here. So I got to use the Pythagorean theorem. 3 squared plus b squared equals 4 squared. So 9 plus b squared equals 16. Subtract a 9 from both sides. If b squared is 7, then b must be the square root of 7. Now, what's negative here? If I'm in that second quadrant, that's 4. This thing here has to be negative square root of 7. That's 3. All right, knowing that, then, if sine is 3/4, then cosine is adjacent over hypotenuse, so negative square root of 7 over 4. Tangent is opposite over adjacent, so 3 over negative square root of 7. I'm not going to leave irrational numbers in the denominator, so I'll hit top and bottom with a square root of 7, and that's what I get. Then if you want the other trig functions, just flip over the ones you got. So if sine and cosecant are reciprocals, so cosecant of theta equals 4/3. Cosine and secant are reciprocals, so flip it over. I'll get 4 over negative root 7. Rationalize my denominator. And then for tangent and cotan, I'm going to flip over the original one so that 3 over root 7 will become negative root 7 over 3. Ooh, look at the next one. The next one has some funky looking numbers in it. And it gives me both a cosine and a tangent, but doesn't tell me anything about what quadrant it's in. Well, what do we know about cosine? Cosine is the x-coordinate. So if the cosine is positive, that must mean I'm either in quadrant 1 or quadrant 4. Right? If tangent is negative, that means sine and cosine have opposite signs. So they have opposite signs in quadrant 2, and they have opposite signs in quadrant 4. So that's how I found out that I'm in quadrant 4. Because the cosine is positive in quadrants 1 and 4. That's the x-coordinate, right? To the right of the y-axis is positive. Tangent is negative when the sines and cosines are different signs. So that's in quadrants 2 and 4. So I must be in quadrant 4. All right, so here comes the fun. In quadrant 4, I have an angle. It says the tangent is negative 5/4. So tangent is opposite over adjacent. So the opposite is negative 5. The adjacent is 4. And part of the work is kind of already done for me in that if I want to find the third side, a squared plus b squared is c squared. And you notice the numbers I get are 25 and 16. They add up to 41. So this thing here is the square root of 41. All right. So what am I missing? I'm missing sine. Sine is opposite over hypotenuse. So the sine of theta is negative 5 over root 41. And again, rationalize my denominator, so I get negative 5 root 41 over 41. And then if you want the other ones, just flip the ones you got. Secant is going to be the reciprocal of cosine. Cotan is the reciprocal of tangent. And cosecant is the reciprocal of sine, although when I find it, what I would do is I would go back to this form of it and flip, so you don't have to re-rationalize your denominators. So cosecant of theta is root 41 over negative 5. All right, the next thing that comes out of this are Pythagorean identities. When we formed that unit circle, we had said that x squared plus y squared was 1, right? X squared plus y squared equals 1 is the equation for a unit circle, right? Radius is 1, centered at the origin. But if x is equal to cosine, let's replace that x with a cosine. Let's replace that y with a sine. And we come up with a statement that says the cosine of theta squared plus the sine of theta squared equals 1. Now, we sometimes abbreviate it like this. Rather than writing cosine of theta in a set of parentheses, we write cosine of theta squared like that, and we write sine of theta squared like that. That's a way for us to not have to write the parentheses, but at the same time to understand that it's not the theta that we're squaring, It's the entire cosine of theta and the entire sine of theta. So that is the very basic, what they call the Pythagorean identity. Sine squared plus cosine squared equals 1. As you go through the course, you're going to see that hundreds of times, I'm going to guess. It's one of those things that's sort of the foundational building blocks of trigonometry, that sine squared plus cosine squared is 1. All right, once you know that, it turns out that you can write other identities as well. You can write that 1 plus tan squared is secant squared and 1 plus cotan squared is cosecant squared. Now, where did those come from? They all came from sine squared plus cosine squared equals 1. So if you're in the middle of doing an assignment or you're working on a test or you're trying to figure out how these things are related to each other and you don't remember whether it's 1 plus tan squared or 1 minus tan squared, go back to the original identity. Sine squared theta plus cosine squared theta equals 1. What if I divided everything through by sine squared theta? Sine squared over sine squared is 1. Cosine squared over sine squared is cotan squared, right? Because if sine squared over cosine squared is tan squared, flip it over, you get cotan squared. The reciprocal of sine is cosecant. All right, so what I just did is I just did this one down the bottom here. All right, do it again. Do sine squared theta plus cosine squared theta equals 1, except this time divide through by cosine squared. All right, sine over cosine is tangent, so sine squared over cosine squared is tan squared plus 1. The reciprocal of cosine is secant squared. So I just did that one. So as long as you remember that sine squared plus cosine squared equals 1, you can get the rest of them from that identity. So let's try a couple of them, show that it works. So this one says, show the Pythagorean identity holds for theta equals pi over 6. So start by finding the sine and cosine values at that point. Ooh, do I have to go all the way back to my unit circle? Why not? Here's my unit circle. At pi over 6, the first coordinate, the cosine, is root 3 over 2. The second coordinate is a half. So here, let me find some space. At theta equals pi over 6, the cosine of the angle is root 3 over 2. The sine of the angle is a half. So cosine squared plus sine squared, does that give me 1? Well, remember when you square something, you square the top and the bottom in a fraction? So square root of 3 squared is 3, 2 squared is 4. Over here, 1 squared is 1, 2 squared is 4. 3 quarters plus 1 quarter is 4 quarters, which is 1. So sure enough, this is, actually this is cosine. So this is cosine squared of theta. This is sine squared theta. Cosine squared plus sine squared equals 1. So we can actually put numbers in there, and it holds. All right, the other one says if the sine is 1/3, use the Pythagorean identity to find cosine if theta is in the second quadrant. So the sine of theta is 1/3. What's our formula? Cosine squared theta plus sine of theta squared equals 1. So cosine squared theta plus 1/9 equals 1. Well, if I subtract the 9th from both sides, 1 is the same thing as 9/9. So 9/9 remove 1/9, I get 8/9. So cosine squared theta is 8/9. Now I should take the square root of both sides, because the question asked me to find the cosine of theta. Remember when I take the square root, I put a plus minus in front of things. And I can separate the top from the bottom, right? Make it the square root of 8 on top, square root of 9 on the bottom. Well, square root of 8 simplifies to 2 square root of 2. Square root of 9 is 3. But now the question asked me something very specific. It said theta is in the second quadrant. So if theta is in the second quadrant, what's true about the second quadrant? Here the cosine values are positive because the x's are positive, but here the cosine values are negative. So my answer is going to be negative 2 root 2 over 3. Because it told me it was in the second quadrant cosine is negative. Why? Because the x's are negative and the second quadrant is to the left of the y-axis. All right, the last bit of this deals with something we call periodic functions. Periodic functions have the same pattern that repeats over and over and over. So my example was if you plotted the number of hours of daylight for a year, it's going to increase and then it's going to decrease. So in June, you hit the time where it's the longest amount of daylight for a year, and then it decreases until it gets to December 21st, 22nd is the shortest amount, and then it begins to increase again. Every year, increases, decreases, increases, decreases. So the pattern repeats every 365, or really with leap year, 365 and a quarter days. Wherever it starts, it goes up, it goes down, it comes up, and that's one period. And then it starts the next period. It goes up, it goes down, it comes back up again. So in plotting number of hours of daylight, it repeats year after year after year in that way. It's called a periodic function. And shockingly enough, sine and cosine are periodic functions. So the definition says if the pattern repeats the same time, like if every 365 days you looked at that graph, you wouldn't be able to tell one year from another. It would just look the same. So how long does it take before the pattern starts to repeat on that unit circle? Here, I'm going to give you this unit circle because it's closer. So how does the pattern go? It starts at 0, it goes up to 1, it comes down to 0, it goes down to -1, it goes back up to 0. So it looks like it takes 2 pi before I include all those values, right? Before the pattern starts to repeat again. So it starts at 0, it goes up to 1, down to 0, down to -1, up to 0, up to 1, down to 0, and so forth. So it takes 2 pi radians, right? That's the angle measure, before it begins to repeat. By the way, the same thing is true for cosine. So the period for sine and the period for cosine are both 2 pi. What is the period for tangent? Well, that's a little bit trickier. So remember, tangent is sine divided by cosine. So tangent is sine divided by cosine. So over here, the tangent of pi over 4 is equal to 1. By the time I get down here, the tan of pi over 4 is 1 again. The tangent over here is 0. Right? 0 divided by 1 is 0. Over here, the tangent is also 0. And so the tangent is positive. The tangent is negative. It goes back to 0. Then the tangent is positive. Over here in the fourth quadrant, the tangent is negative. Then it goes back to 0. So the tangent repeats a whole lot faster than sine and cosine do. The tangent goes from 0 to 1 to 0 to 1 and goes positive and negative within that pi. So the period for tangent is actually pi. Every pi, the tangent function repeats. So whereas for the period of sine we get 2 pi, period of cosine is 2 pi, the period of tangent is just pi. And this may not make a whole lot of sense right now. When we start graphing these, I think it'll make more sense because you'll be able to physically see what those graphs do. So this is just telling you that for a periodic function, you can take whatever the value you have and add a multiple of 2 pi, and for sine and cosine, you'll get the same thing. For tangent, if you add a multiple of pi, not 2 pi, just plain old pi, you'll get the same thing again. And the last little bit on here is just a unit circle that's typed up. This unit circle is also available up on Canvas, and it's got everything labeled in degrees, radians, and then there's your sine and cosine on the outside there.